So the way I'd like to teach the class today is like a storytelling. Okay, so in the final, it will be the same like the midterm. You will have 5 circuits or 5 questions, circuit analysis, and you will have one multiple choice question. Okay, the multiple choice will be like about the sensors. We started with the temperature measurement and differential amplifier and instrumentation amplifier will be with that section. The question or the first circuit question will be the op amp. Now, let's start. Now, the op amp, as we know it, with the most common configuration that we have is the inverting amplifier. So if this is your V input, this is your R1, this is your R2, and here is your output. And we said that the output over the input, which is the gain equal to minus R2 over R1. This is the gain. Now, this gain can be anything. You decide, select the value of R2 and R1, and then you get the desired gain. If you want to have an amplification of 100, select R2, for example, 100 kilo ohm. Your R1 is 1 kilo ohm. So you will get a magnification of 100. Then your output will be 100 times your V input. So question is, so what's wrong with the op amp? Why we need to learn other types of amplifiers? Which is a very, very valid question. And that is the story I want to tell. As we move from one amplifier to another amplifier, we need to understand the justification in as much simple language as I can, because there are some certain advanced topics meant for electrical engineering students. I will try to simplify the language, but at least you understand the logic and why we are doing this. So let's start with the differential amplifier. Why to have differential amplifier? If you recall, if using sensors, for example, string gauges or temperature sensors, most of the time the sensor location and the instrumentation locations are very far from each other. So there should be some connection. So there will be some wire connecting between the sensors and your measurement system. Now, when you have a long wire, this long wire is basically acting like an antenna. Antenna, it will pick up any radiation, any electromagnetic waves from anywhere. And as we know it, there is tons of sources of electromagnetic waves uh, spread all over the place. So all these waves will be collected by these wires, and hence you will have a huge amount of noise. We will talk about filters at the end of the course as a way to get rid of noise, but there is another efficient way that we will discuss, and this is comes the differential amplifier. So if we can amplify, now when we have an op amp, this op amp has 2 legs. So each leg will be coming from the same location. So we can assume safely that the noise is the same as these 2 inputs. So if we can subtract these 2 inputs, then we can subtract any common noise between them, and this can reduce the noise to certain extent. So, and here is the word differential comes. Differential comes from the word from difference, from trying to take the difference between the 2 inputs so that you will cancel the common noise between these two inputs. So this is why we need to use differential amplifier. And let's analyze this circuit. Okay, so we will have 2 inputs here as such, and we want to see what is the output with respect to the input. So remember, our objective is to find a circuit that gives me an output that is equal to a gain, my amplifier gain, times the difference between these 2 inputs, so that I will not I will cancel the noise. So let's apply KCL here. Now this voltage is V2, so this will be also V2. So apply KCL at V2. So we'll assume the currents are leaving. We have three branches, one, two, three branches. Now, differential amplifier is actually, as we will see, is an operation amplifier modified a little bit. That's all. There is no difference. This is why we have to learn the op amp. So assuming the currents are leaving, and the currents here is equal to 0 as we know it, so we have V2 minus V1 divided by R1, the current to the left, plus V2 minus V out over R2, current on the top, is equal to 0. So I will take V2 as a common factor. You will have 1 over R1 plus 1 over R2, plus we will have sorry, minus V1 over R1 equal to V out over R2. I will just collect terms, so I will add these two together. So we will have V2, take the common denominator, so this becomes R1 R2, and this becomes R1 plus R2 minus V1 over R1 equal to V out over R2. So I will multiply everything with R2. So what we will get here, we will have minus R2 over R1 times V1 plus R1 plus R2 over R1 V2 is equal to your V out. Now, this, we can say that this is equal to minus R2 over R1, V1 plus 1 plus R2 over R1, V2 equal to V1. So actually, we didn't get our objective yet. Why? Because V1 and V2 are multiplied by different factors, not the same factor. So if I can somehow, this V2, instead of having it as 1 plus R2 over R1, if I can change this somehow to R2, this is R1, over R1, then we will have R2 over R1 as a common factor, and then you will have R2 over R1, which is the gain, of the inverting amplifier. But here I will not multiplying by V1, but instead by V2 minus V1. This is the whole idea. So that is the objective that we want to achieve. So let's see how we can do this. So this is my circuit. We want the output to be like this. C, which is the gain, and in this case, the gain will be R2 over R1, the same gain we have for the inverting amplifier, times the difference between V2 minus V1, the two inputs. So when we subtract them, we will get rid of the common noise between the two inputs. Okay. So let's see here. So as I mentioned, if I can change 1 plus R2 over R1 to R2 over R1, then we achieve the goal. We know that if we 1 plus R2 over R1, this is nothing but equal to R1 plus R2 over R1. So if I can multiply this somehow with R2 over R1 plus R2, if I can multiply this, so in this circuit here, if I can introduce something here, some circuit here somehow, so that this input, instead of having it as V2, it will become equal to, multiply it by R2 over R1 plus R2, then I will achieve my goal. So this looks somehow familiar. R2 over R1 plus R2. This is nothing but a voltage divider. Remember, when we have a voltage source and we have R1 in series with R2, this output voltage here, V, is equal to your V input times R2, this voltage, divided by the summation of the two, R1 plus R2, which this is what we want. So if we introduce between this input and the amplifier a voltage divider, then our problem is solved. And this is what exactly we do. So instead of connecting V2 directly to the operational amplifier, I will connect it to an R1 in series of R2. Someone may say, how come it's in series? This node is shared with a third branch, but we know that the current here is equal to 0. So basically, this current as this current are the same. So if these two currents are the same, then R1 and R2 are in series. So now the input I am putting inside my op amp here is not V2, but instead V2 times R2 over R1 plus R2. Then my amplifier will act as I intended. So this is the final design. This is the differential amplifier. It's basically an op amp, but it will have two resistors. This is inverting amplifier, nothing different than the circuit I just mentioned at the beginning of my class today. However, I will add another circuit, which is R1 in series with R2, so that we will get our output. Now this becomes R2 over R1 as we intend to have, and this is my differential amplifier, R2 over R1 times V2 minus V1. So now when you hear the word differential amplifier, don't get scared. This is nothing but an operational amplifier. I'm just connecting the same R2 and R1 as a voltage divider, as simple as that. And if you analyze this circuit, you will get this output. This is a nice exercise. If you go, it's a just simple op amp circuit, nothing different. You will get this. Now, once you get a circuit like this in the exam, you don't need to analyze it. This is a differential amplifier, and you have to. This R2 over R1, this is R2 over R1. So if this is the ratio of these two are there, then this becomes a differential amplifier. What if it is not? What if this resistance is not R2, it is R3? Then we don't have a differential amplifier, and then we need to analyze the circuit as we will see in this example. Here it says find the output voltage for the following amplifier. So this is 5 and 1, this is 8 and 1. So this is definitely is not a differential amplifier because this ratio is not the same. Then the question says if this 8 kilo ohm we change it to 5 kilo, what will be the output? If we do this, then we will get the differential amplifier and we can get directly the output. So this is the two inputs, 2 volt and 3 volt here. And what we want to get now, we want to get the output. So here, for this circuit in part A, we need to analyze it. Okay, so I will call this is V and this is V. These two unknown voltages, V. So I will call this is node 1 and this is node number 2. So apply KCL at node number 1 here. So we will have V minus 3 divided by 1K plus V minus 0 divided by 8K is equal to 0. Okay, so here from if you analyze this, so let me multiply by let's say 24,000 or 24,000 or 24K. Oh, no need for 24K actually. Let's multiply by 8K only. 8K will be sufficient. So multiply by 8K. So here we will have 8V minus 24 plus V equal to 0. So we will have here 9V equal to 24. So this means that your V is equal to 24 divided by 9. This becomes 8 over 3 volt. So now we know that this voltage is 8 over 3 volt. Then this voltage becomes 8 over 3 volt. So now apply KCL at node number number 2. So this become, now we know this voltage, which is 8 over 3. So this becomes 8 over 3 minus 2 over 1K, which is this current. And then here plus 8 over 3 minus V out, which is our unknown, divided by 5K equal to 0. Now, when we solve for this, you will find that your V out is equal to 6 volt. Okay, now let's go for part B. Now I will change this to 5 kilo. If I change this to 5 kilo, I don't need to do any analysis. Your V out is equal to the 5K divided by the 1K times V2 minus V1, or 3 minus 2, and this is equal to 5 volt directly. So for the differential amplifier question, you don't need to do any analysis. Directly you will buy this, and when you go into the market, you will buy this as one chip that will have these resistors internally. You don't have access to them, so you just have access to the input. So it's like an op amp, but it has this internal resistance inside fabricated. Why fabricated inside? Because something very important. It's very hard when you buy those loose resistors to have exactly the same 5 kilo ohm. So because remember, the ratio has to be the same, otherwise you will not have a differential amplifier. But when you fabricate them inside the chip, you have a very good control on them. So this is why you usually everything is actually fabricated inside one chip, so you don't see these resistors. They are actually internally, so you have no control over the gain. You don't have a control over the gain. You will actually have a specific gain of that, and this is one of the disadvantage of the differential amplifier. But it's not that only. There is another severe disadvantage with the differential amplifier, and this is why we move now from the differential amplifier to the instrumentation amplifier. Now, this looks familiar to us. This is a Wheatstone bridge. And this Wheatstone bridge could be using an RTD, one of the temperature sensors. So we have here V1, we have V2, we have R2, R1, R2, R1. And remember, the output of this is nothing but the Wheatstone bridge, if you recall. So the output that we have measuring V out is the difference actually. So it's V2 minus V1. This is our output. Now I am entering this. My output is my input to the amplifier. And now we understand very well why we use the differential amplifier, because actually the Wheatstone bridge, which is one of the most important circuit in instrumentation for us, its output is actually a difference between two inputs. Okay, so this is why it's very, very important to subtract them so that you will get this, get rid of the noise. Okay, so what's wrong with this? Everything looks good. There is one issue. The issue is that we need to solve now to go for the last amplifier, that the input impedance is very small. Okay, first we need to understand what is input impedance, and then why it's a problem when it is small. So this is to start with. So for example, in this brand, this is your V2 and this is your V1. V2, the input impedance is the impedance this can see, your input. Now we know that this is I equal to 0. So this is like it is disconnected. There's no current can enter inside, because here you have an infinite resistance. So the resistance that we have will be R1 plus R2. This is your input impedance. Now your input impedance is small, regardless of the value. Usually they are in kilo ohms or tens of kilo ohms. That's all. This is not a good value for input resistance. The question is why? Why this is not a good thing? Okay, let's first agree about one thing, and I will mention why. Any measurement system that you have, it has to have very, very high input impedance. Why? Because this measurement system should not consume the current from the circuit. So what if it consumes? Let me give you a simple example. Imagine that we have this simple circuit. I have a voltage supply, and this is Vs. This is your R1, and this is your R2. And we are measuring this voltage, V. We know this is a voltage divider, so we know that this V out is equal to Vs times R2 over R1 plus R2. Now, this is with the assumption that R1 and R2 are in series. Okay, we know that the voltage division we can only apply it if they are in series. What does it mean in series? It means that this current I and this current is the same. Now, imagine I am bringing my voltmeter to do the measurement. So I'm bringing here a device to measure. So we connect two leads between these two terminals to see how much the output voltage. Now, once we connect a circuit, there will be a current here. So as a matter of fact, this current will not be the same as this current. Why? Because we have a current going on. This is why for this measurement system, I want the input impedance to be very, very, very high. Ideally is infinity, so that the current that goes here is equal to zero. I don't want this measurement system to have a small resistance. Otherwise, it will take from the current in the circuit, and the whole circuit will be changing because my measurement circuit is interfering with my circuit, and it should not. It should measure the voltage without consuming any current from the circuit. This is why I need this to have a very, very high input impedance. I hope with this you understand the basics. I don't want to go in details, but this is what you want in any measurement system, measuring the voltage, that you need its input impedance to be very high so that it will not load, it will not consume the current from the circuit, and all the assumptions you have will be wrong now because the current that the circuit is consuming is significant. Okay, so that's all. So this is why we need to have to move from the differential amplifier into another amplifier. We call it the instrumentation amplifier. So all we need, this is nothing but my differential amplifier. So what I need to do, instead of having V1 and V2, which is my differential inputs, connected directly, I will connect them through a buffer. The buffer is a circuit that will allow the voltage to flow, the same voltage to go, so it will not affect the voltage, but it has a very, very high input impedance. And this is the instrumentation amplifier. So basically, what is a buffer? Remember, when we discussed the op amp, we have this configuration. We call it voltage follower. Let me just refresh your memory and go back. When we first discussed the op amp circuits, we said that, yes, this circuit, yes, this is the voltage follower. We said that V out over Vs is equal to 1. And we said, what is the benefit of this circuit? I said we'll talk about this later on. Okay, so this is a circuit that the V out and Vs, V output or V input, are the same. Now, it has a big advantage. It has a very high input impedance. Why? Because remember, this is the current input. This is the input current. This is the current coming from the circuit to here. But this is what? This is an open circuit. So this is now the amplifier or the measurement circuit will see an input of an amplifier, so this becomes extremely high. So it will not take any current from the circuit here. The current that goes here is equal to 0. So this is almost is equal to infinity. So this is why this is extremely important part of a circuit, which is the voltage follower, or sometimes we call it, or the more technical term, it is the voltage buffer. So this is what we will connect here. Okay, so here this is the instrumentation amplifier, your two inputs VA and VB. Now we will have a buffer here in between. Now everything here is integrated. You have no access to this. This is all one chip. Unfortunately, I mean, we have very nice experiments using this instrumentation amplifier, and to see the difference between the op amp and the instrumentation amplifier, you see there is a lot of noise there. Here it has two functionalities. First, it has a differential functionality, so that it will get rid of the noise. Second, it will have a very high input impedance. Now, but still here we have one small problem. I just mentioned a little bit when I talked about this amplifier. We said that this R2 and R1, R4 and R3. Now R2 over R1 here is equal to R4 over R3. So they are the same ratio. It could be the same values, specifically R2 and R1, R4 and R3, or the ratio could be different. This could be, for example, 10 and 2. This is 20 and 4. Same. You will get the same thing. Now, everything here is enclosed. What if I want to change the gain? Because the gain here is R2 over R1, which is 5. What if I want to have a different gain? Should I go and buy another differential amplifier every time I want to have a different gain? I will go and buy, sorry, an instrumentation amplifier. Or is there a way I can do the control? And here it is how we do the control. And this is the last thing in our circuit. So you have your inputs here. This is basically your voltage followers. But here we have R5, R6, and RG. And this RG is externally connected. Everything else is integrated, but RG is externally integrated. And RG is the one that we use to control the gain, as we will see. So let's analyze this circuit. Let's understand it with our understanding of the op amp. Now, this is our, forget about this circuit, the blue one. Let's just look to the circuit from here to the right. Forget about what is in the left. So this is a differential amplifier. And we know that for this differential amplifier, now R2 over R1 is equal to R4 over R3. So we know that your V out without any analysis is equal to R2 over R1 times VA dash, which is this one, minus VB dash. This is your output. Okay. So this is the output that we have here. Now, this is differential. Now, let's go back and let's start to analyze the circuit. So we'll have here, this is the circuit. Now, we will call this current IG. I will call this is VA, and this is your VB. Now, why we call this VA and VB? Because we have here VA and VB. Remember, this voltage and this voltage is the same. It's the same node. So this is VA actually. So this voltage is the same as my input voltage, VA. Same thing here. This voltage and this voltage are exactly the same. So this VB and this VB are exactly the same. So now here we can say that IG, Ohm's law, IG is this current. So it's basically VA minus VB divided by RG. This is the current. It is VA minus VB divided by RG. But now we want to somehow relate this input to this input, because this is the output that we will have here. Okay, excellent. So what is VA dash minus VB dash, which is this voltage, this differential inputs here? What is their difference? So this node is basically is this node, and this node is basically is this node. So this is equal to, now the current that goes into here is equal to 0. So if this is IG, it's the same current that goes through R6 and R5, because there is no current going here, there is no current going there. So all of this is exactly the same current. So the voltage difference between this point and this point basically is equal to your IG times the summation of R6 plus RG plus R5. It is all these resistors because they are in series, because there is no current going here, there is no current going there. So IG that we assume between these 2 points is exactly the same IG that goes from actually the starting from the branch to the end of it. Now let's assume that we will have R5 is equal to R6. Make things simpler. Then your VA prime minus VB prime is equal to IG times 2R5 plus RG. Okay, very good. Now, your output, V out, we said it's equal to R2 over R1 times VA prime minus VB prime, which is equal to this, equal to IG times 2R5 plus RG. This is what we reach here. R2 over R1, IG times R2, R5 plus RG. Okay, now what is IG? This is R2 over R1. What is your IG? Let's go back here. We know that our IG is VA minus VB over RG. So this becomes times VA minus VB divided by RG times 2R5 plus RG. So let's collect terms here. We will have, this is R2 over R1 times, take this one here, this is RG, is equal to 2R5 plus RG divided by RG times VA minus VB, which is equal to R2 over R1 times RG over RG is 1 plus 2R5 over RG VA minus VB, and this is the relationship of the instrumentation amplifier. Recall that for differential amplifier it was V out equal to R2 over R1 times VA minus VB. This is the output of what? The differential amplifier. So we'll have here R2 over R1 and VA minus VB. So it's the same thing, except we have now this extra term. Now this extra term will have RG. RG is an external resistance that I can play with. I can increase, I can decrease. So I will have a control over the gain. So now my instrumentation amplifier can do everything I want. It will have no noise or less noise because of the differential part in the circuit. Second, it will have high input impedance, which doesn't available in the differential amplifier, but it is available in the op-amp. Remember, the op-amp has a high input impedance itself, but the differential does not because of the branch that we needed to connect to make a differential amplifier. Third, I have a control over the gain. So everything in instrumentation that I want is available in the instrumentation amplifier. And this is why this is the standard amplifier. We use it in circuits, and every instrumentation system will have an instrumentation amplifier, but it is built on the understanding of the op-amp. The op-amp is the main building block of the differential amplifier and the instrumentation amplifier. So with this, we finished the whole story of the amplifier from the beginning, why we need an amplifier, and the progress of the amplifier until we reach it to the last stage of the instrumentation amplifier. So what's next? We will be starting from tomorrow talk about capacitors and inductors, which is totally different devices. But as you know, Thursday and Friday is a Canada Day, so I take this opportunity to congratulate all of you. Happy Canada Day. And so we will be off, so we will just start the topic on Tuesday, and then so there'll be no tutorial this week, and then we will continue or start again on next week. Enjoy the summer, be careful of the heat, and talk to you tomorrow.